Hello and welcome. In this video, I'll be covering section 7.4, which is over the inverses of trigonometric functions. My goal for you by the end of the video is to be able to find values using those inverse trig functions, to be able to simplify expressions that involve either compositions of trig within the inverse trig or inverse trig within the trig, and then simplifying expressions that involve other compositions that have values inside or ratios provided or angles provided without the use of a calculator, so that'll be more referencing like unit circle ratios, and then to be able to simplify expressions that involve trig and inverse trig, but this time only providing ratios, where I could then utilize potentially a triangle to come up with other values. So if you recall from prior lessons earlier in the year, to find an inverse of a function, technically what would happen is the x and y values would both swap. So if we think about the original graphs for sine, cosine, and tangent as examples here, as you can see on the screen, remember we also had what was called the horizontal line test that let us know whether it was a one-to-one function. So as you can see with all three of these graphs, or what you would maybe hopefully remember about those graphs, is they definitely do fail the horizontal line test, meaning they are not a one-to-one function. Therefore, if I were to swap all of the x's and y's, technically the result that would happen, or the inverse of those, would not actually follow the function rules, meaning I would end up having multiple outputs for the same input. So in this scenario, what we'll end up doing, and again visually as far as like what would happen, if you recall, it would be like a reflection over the line y equals x, as you can kind of see down here at the bottom. If I have that happening here, it creates a wave that goes back and forth across the y-axis, or with a tangent it kind of creates some what look like almost cube root graphs, I suppose. Or again, it just fails vertical line test over and over and over, so technically those are not functions unless I restrict the actual domain. So as an example, which will happen here on the next slide, if I took like say this sine graph right here and I just was able to cut everything from there up and everything from here down, if I were able to just cut off all of that, now notice it would pass the vertical line test, or at least that vertical red line actually would cross over. Now why I would cut off those parts is mainly just because I would want to try and find a way to keep zero involved somehow, some way, and ultimately I just kind of go from wherever it kind of first doubled back on each other and use that part as like either a start or a stop for what would get cut off. And so what that creates, as you can see, if I get rid of that here for this slide, if I go to the next one, it creates these three graphs. If I did a very similar thing for the other functions, either sine, cosine, or tangent. And so if I look at what's happening here, notice it does give us a restricted range of possible values. So the range for each of these is actually kind of think like that's what my answers are allowed to come back between. Now as far as the domain is concerned, sine and cosine, I hope it's reasonable that if we think of the unit circle, the largest and smallest values I could get back from the unit circle were +1 or -1. So since I'm swapping the inputs and outputs, now it's more I can only plug in numbers between -1 and +1, and it will only give me answers back, as you can see here, inside of the range from -π½ to +π². Technically we could also convert that into degrees, where I could say that that would be something between -90 degrees and +90 degrees, and technically can include both of those values. For the range for the arc cosine, I guess that's another thing to take note of here, is we also have, as you can see with this, two different ways to represent the same function. The top of which is more just utilizing inverse notation, so it kind of looks like a power of -1, when in fact it just is representing an inverse. The actual name of these functions are the arc sine, the arc cosine, and the arc tangent. And what's important here to kind of think about was what would go into a trigonometric function is an angle, and what would come out as a ratio. So since I'm flipping the script on that, now it's going to be what goes in as a ratio, and what I get back is an angle. Hence why, as you can see here, all of our ranges, if I continued on, the next one would be 0 to 180 if I did that conversions from degrees to radians, or technically from radians to degrees. And then the last one, what's a little bit different compared to the sine, is I still get -90 degrees to +90 degrees, but this time I can't include them because the tangent actually is undefined at those values. So it gets as close to those values as possible, but doesn't actually include them. But again, kind of going back to the how should I be thinking about these functions? Well, whatever goes inside of the function will always be a ratio. Whatever comes back out would need to be an angle that falls within these specific windows depending on the specific function. So as far as another visual for what's going on there, where the angles can come back from is kind of what's representing here with this kind of the arc that's been drawn, or at least kind of colored in red. What's going to be a little bit peculiar is all of the fourth quadrant angles that happen for the arcsine and arctangent. I actually need to think of as they're negative angles, not so much positive angles. So in other words, I don't go all the way around to get there. I actually just go straight down from the origin. So if we think of where 330 degrees, for example, would be, technically I want to think of that as more like negative 30 degrees or negative pi 6 if I was talking radians. So that, for the most part, is really the trickiest thing about these specific functions is, on occasion, at least the arcsine and the arctangent will give us negative angles back. We need to then be able to reference appropriately, especially if we're trying to do it without a calculator, the actual angle that I can be. So again, arcsine is allowed to be angles in the first or fourth quadrant, or arctangent's the same, except for I can't include the actual values on the y-axis. But all of the ones in the fourth quadrant I need to think of as negative angles, not positive angles. Arc cosine out of these three is technically going to be the easiest one. It just comes back in either the first or second quadrant, and all of those angles are consecutive. In other words, I don't have to worry about any sort of negatives, because from there it's only going to go up from the x-axis even if I went into the second quadrant. So arc cosine in general, again, because the range is from 0 to pi or 0 to 180, that usually is the easiest for most to comprehend, because I don't have to think in terms of the fourth quadrant being negative angles or anything weird like that. So when it comes to some actual examples of how we would simplify some of these things, potentially utilizing the unit circle, notice again in all three of these examples here, what's being plugged in. Didn't throw parentheses, but we can have parentheses around it, or we can have them not be there. But notice what's inside of each of these functions is a ratio, so my answer that's coming back should come back as an angle. So that's kind of my goal, is to figure out what angle actually has that value, but I also need to be mindful of what's the range allowed for each of these functions. So remember, the arcsine function was something that needed to fall on the right side here, so one of those two quadrants. In this scenario, though, it is a positive ratio, so I know it's going to be a positive angle. So I look for where is the y value equal to a rad 2 over 2. Hopefully we would relatively quick realize that that would be a 45-degree angle. Or in radians, I could say it's pi fourths. So depending on what a specific question would want, it would be one of those two answers. But again, one of them's just, well, I mean, it's the same angle, but they're just using different units to represent it. So if we go with the cosine, cosine again is going to have to fall in one of these two quadrants. This time, though, I do see a negative sign. So that kind of tells me for sure it's going to have to fall in this second quadrant here. So if I think about where would cosine have a ratio that's negative 1/2, well, that means it shouldn't be very far horizontally. So that means that more than likely is this angle right here, which would be 120 degrees, or I could also write that in radian form as that would be the 2 pi thirds angle. Now arctangent, similar to the arcsine, it's got to be in one of these two quadrants, so either the top right or bottom right. And the bottom right is technically where it would need to be negative angles, so I need to picture this like I'm going down that direction if I'm actually going to have a ratio that would be negative. This one actually is a negative ratio. It's not a very steep one. Remember, tangent always went with like the slope, so since that's actually the smallest out of those options, it's going to be the one that's not so steep. So now if I think in terms of what angle would that actually be, even though it would be 330 on the unit circle, it actually is something we need to reference as negative 30 degrees or negative pi 6. So again, the trickiness of the arcsine and arctangent is anytime I have a negative on the inside, I just need to picture, okay, it's going to go down into the fourth quadrant, so that needs to come back as a negative angle. Now all of these were supposed to be done without use or can be done without the use of a calculator, but we could also confirm whatever we have. I think it's probably easiest to confirm if you keep your calculator in degree mode. Radians gets a little tricky because knowing what the decimal equivalence of pi fourths is, this is a little tricky. I don't think any of us have that memorized. But we could type in pi divided by 4 and figure out its decimal and compare that way. But again, if it's degrees, more than likely it'll be a little easier to at least check your answer if need be. And ultimately we would just make sure that the mode matches what we want the answer to come out in, and then we just press the buttons. So like arc sine of the square root of 2 over 2 for this first example, if I pressed enter in degree mode, would actually give me 45 degrees. So we can kind of use that to our advantage to just double check ourselves before we move on. But again, for all of these three, since all of those ratios were from the unit circle, I shouldn't need to use a calculator to actually be able to come up with its exact value. So speaking of using a calculator to check your answers, notice this question actually requires us to use the calculator, since this is now a ratio that's not a familiar one from the unit circle. So as far as like how do I do that using the calculator, this hopefully will help clarify that question. I do need to, anytime I do any sort of use of a calculator, especially when it comes to doing anything with a trig button at all, whether it's the original cosine function or in this case it would be the arc cosine function or the inverse of it, I need to be aware of what mode my calculator is in. So this one wants me to actually model both. So I'll have one answer that will be in radians and another answer that's going to be in degrees. So I'll just go ahead and get kind of my answers set up here in some way, shape, or form. And if I go ahead and bring a calculator up, it's going to be now do the inverse cosine of, this was negative 0.2689 was the ratio that they provided for us. Do a quick glance at the top of the screen. I'm currently in radian mode, so this is going to give me first and foremost my radian answer. So this would come back approximately 1.843. So 1.843 radians, which if you recall, halfway around the circle would be pi, which is like 3.14 radians. So the fact that this is less than pi should hopefully make sense, because arc cosine, if you recall, is supposed to be somewhere in one of the top two quadrants. So the fact that that came back less than 180, or sorry, what would have been pi over here, I hope makes sense. But I think the degrees one is probably going to be easier to kind of picture what that actually did. The fact that this is negative kind of tells me that it should probably be in this second quadrant. So if I went through and found what actually half of pi would be, which I want to say is like almost 1.6-ish, the fact that that's a little bit more than that hopefully is reasonable. So it probably is an angle that would be right about there if I had to approximate it. But again, we can go ahead and just double check this in degrees. That might be even easier to picture. So all I have to do is go into the mode, go down and highlight degree, quit back out, and since I've already typed it in, I may as well take advantage of just going up and highlighting it, pressing enter again. Since I switched the mode, it's going to give me the other value that it could have been, in this case 105.6 degrees approximately. So 105.6 degrees, which again, if we look at the estimation that we had there in radians, that was 1.6. In degrees, this is 90 degrees up here. The fact that that was just a little bit more than 90 degrees seems reasonable for our, I guess, approximation. But we could also think unit circle wise, this is -1 as a ratio. Somewhere about in the middle would be -0.5. So since this was -0.26, it should have been a little bit closer to the y-axis if we think in terms of what the angle should have been, because again, cosine goes with the x's after all. But again, this basically comes back to the idea of, since it was negative, I knew for sure it wasn't going to be in the first quadrant, and since the arc cosine had the restriction of it's got to be in the top two quadrants, or from 0 to 180, that's why the calculator gave me back the answers that fell in the ranges that we ended up getting. Alright, so moving on to now maybe the second type of way that these functions can get involved, or at least all of the inverse trig functions, is I could now do the compositions. Now, if you think about why would we want to do compositions, ultimately an inverse function should essentially quote-unquote cancel whatever its original or other function would be. So for example, if I wanted to cancel sine, I would utilize the inverse sine or the arcsine function. Similarly, the cosine, I would use the arccosine, and tangent, I would use the arctangent. But for these specific problems, right, it doesn't necessarily always just straight up cancel and just leave what's inside. I do have to, because some of the inverse trig functions come back with slightly different I guess ranges. Since sine can technically give us a whole bunch of different answers, the arcsine only is allowed to give me a certain number of answers in the first or fourth quadrant. So I do have to be very mindful of what the outside function is. If the outside function is trig, everything for the most part stays pretty honest and true. If it's the inverse trig, that's when I might have to worry about I only can answer in between whatever the range of that specific function is. So for arcsine, I'd only have answers in degrees at least that would need to fall back between negative 90 degrees and positive 90 degrees. Similarly with arctangent, that would be true. Whereas arccosine is actually, again, it's usually the easier one because it just gives me answers that are already positive anyway. However, if the original angle in the cosine was not in the first or second quadrant, I would need to make sure that I kind of reference the correct of those two options, whether it would be a first or second quadrant. But at least the answers for that come back positive in all cases. It's the arcsine and arctangent that potentially have to worry about those negative values. So again, just pay attention to the details here. It's what's the outside function or what's in front, if you want to think of it that way. If it's just a normal trig function, you're just going to reference what angle, you're going to have an angle that would be going in, and then you're just answering with whatever the ratio is for that specific angle. It's when it's the inverse trig that's out front or is the outside function. That's when potentially I have to worry about maybe my angle is a different place or in a different place than what the original was. So I have to kind of be mindful of does it come back as a negative angle instead of a positive angle, at least for the arcsine and arctangent functions. So if any of that was confusing, I'm going to guess probably most of it was because you haven't seen any examples. Hopefully this will clarify any of those things. So the first two examples, as you can see, the outside function is a trigonometric function, whereas what's inside is an inverse trig, or arcsine or arccosine. The first example here is arccosine. So I do have to be careful of what numbers am I allowed to plug in. Rad 3 over 2 is between -1 and +1, so that is a value I could actually plug into this function. Ultimately, what I would do first is figure out where is that, and so my restrictions for arccosine are the top two quadrants, so that's a positive, so that's just going to be a first quadrant. Which angle has a cosine of rad 3 over 2? Well, that happens to be, if I wanted to do it in degrees, that would be 30 degrees. So ultimately it would just be, I've simplified the inside parenthesis, now let's deal with the outside part. Well, what is cosine of 30 degrees? Well, that takes me right back to rad 3 over 2. So this one does appear to just cross them out, but again, it's better to think through the process because sometimes that may actually be not necessarily the best assumption of how they interact with one another. For example, the next one, if we saw, hey, I've got sine and inverse sine, okay, they cancel each other out, leaves me 1.8. The issue here is the fact that 1.8 doesn't fall between -1 and +1. It actually is too big for that function, so this actually does not exist. So this is just to kind of show that we don't want to necessarily just jump to, hey, they always cross each other out like that. I need to think about, is this allowed first? And then second, what would its value be? And does it in fact turn into the same ratio when I compose it? Because there are going to be times where what if I don't have the exact same? What if it was cosine of the inverse sine where they don't cancel each other? We still can do the composition. It just won't necessarily perfectly cancel, but I could still find its value, which is why we want to kind of think of it that way. Now, the second two examples here, part C and part D, these now have the inverse trig out front, so I have to be mindful of what place my angle is allowed to come back between. These ones specifically are starting with something in radians, so I know that my answer should likely stay in radians. And so for this one, it's going to be, okay, where is tangent of pi 6? Well, I could simplify that and say this is going to be the inverse tangent of its ratio. Well, the tangent at pi 6 is not negative, but positive rad 3 over 3. And now it would be, okay, now inside of the restrictions that I do have, which are first and second, or sorry, not second, but fourth quadrant, inside that restriction here for the arc tangent, what angle would have this same ratio, rad 3 over 2? Well, that's a positive ratio, so that kind of tells me for sure it's a first quadrant. And if I look through the first quadrant, it gets me pi 6, so like you probably assumed, but we could have technically just pictured it like, well, the tangents will cancel each other. But again, if that angle was off a little bit, let's say it was not in the first or fourth quadrant, then I would actually have to reference one of the angles that is in the first or fourth quadrant. Again, that's where things get the most tricky. So this last example is actually one of those kind of tricky things. If we think of where 3 pi fourths is, 3 pi fourths is the angle in the middle over here in the second quadrant, but arc sine is only allowed to give me answers in the first and fourth quadrant. So if we maybe simplify this, this would now be the arc sine of, well, sine of 3 pi fourths in that area is a rad 2 over 2. And now it's okay, out of the first or fourth quadrant, where would that have a positive ratio? Well, that's again going to be a first quadrant angle. And which angle is that? Well, it actually is pi fourths. So the value of this one, notice it didn't just cross each other out and leave what was inside. 3/4 has kind of seemingly magic, by magic, which it wasn't. It was more just the restriction of the function that was on the outside. It kind of forced itself to turn into pi fourths instead of staying 3 pi fourths. So again, knowing what I'm allowed to have as answers is key when it comes to at least just approaching these types of problems. So just be careful with it. And I didn't do one of these examples, but let's say I did have an angle that would have needed to reference into, the, say, the fourth quadrant. I would just make sure that I answer with a negative value for whatever that angle is. So like negative pi 6, negative pi fourths, negative pi thirds would be the 3 possible angles, instead of calling it like 11 pi 6 or 7 pi fourths or 5 pi thirds. So just picturing it as like maybe the first quadrant reflected down might be the easiest way to think of it. Or we could even take advantage of some of the even and odd identities that we've covered in this. A negative inside of an inverse trig function, you could just move out front, and then it would make that ratio now a positive, so you could always just reference the first, and it would just have a negative on front. And again, we can model that in class, or we can model that one-on-one if you need to have some extra examples of this. But I hope the point of me saying, like, just you always need to think about which quadrant or my answer is allowed to come back in for those inverse trig functions. That's really the key takeaway I hope that you're getting from it. So the previous examples were all things that were from the unit circle, or at least reference something on the unit circle. So the next few examples, or to finish out the video, the remaining examples really are going to be ones for what if I have some angles that maybe are not from the unit circle. So as we've encountered in prior sections, when this happens, what we'll often do is draw ourselves some form of reference triangle. So we could specifically draw it into a quadrant that we know it needs to be, or just be mindful of if I needed to have some negatives on some of the side lengths. Remember, the hypotenuse in each of these triangles, if you ever do draw it, will always be a positive value. It's the two legs that potentially might have negatives. So this will happen when I have compositions of functions that maybe don't actually cancel each other down or are not inverses of one another, but we can still utilize the information that's provided to maybe be able to still solve for either what an angle would be or maybe what a ratio would be. So like I said, the remaining examples in this video are going to cover just those situations. So our first such example of that situation here, notice we have the cosine function here of an arc sine function. So notice those are not really inverse relationships. So what we can do is just take advantage of what we should hopefully know about how trigonometry works. The angle on the inside, if I just said that technically is an angle, we could, if need be, kind of picture that the angle is equivalent to that inverse sine relationship. So if we think about how I would move this the other direction, utilizing the inverse kind of idea, where if I move it to the other side, or if I wanted to cancel it, it would turn into the opposite or its inverse function on the other side. That basically is telling me that like sine of that angle has this ratio 3/5. So that's how we kind of build that reference triangle, where I'm just going to say that's going to be my angle A. Now, why did I choose the letter A? It really legitimately was an arbitrary variable. I could have chosen anything really I wanted. So if I wanted to call that X for whatever reason, I could have. So again, that's more just I'm defining it so I actually have a label for my picture. And now it's something where I should be able to now label two sides, in this case the opposite being 3, the hypotenuse being 5, which then lets me solve for the adjacent. And I think we've probably seen a 3, 4, 5 triangle enough times that we would know that that last side must have been 4. But had we forgotten it, it would have been square the 5, subtract the square of 3, and then take the square root of that result, and we would have found ourselves getting a 4. So at this point, notice we've technically taken what was inside, we made the information there. Now it's going to be from that triangle, can we do the cosine? So if I said what is now cosine of that A angle, we should be able to recognize that that would be 4/5 on this, since it was a positive sign inside, or sorry, positive ratio inside of the arc sine. That forced it to have to be, even if it didn't tell me, it forced it to have to be a quadrant 1 angle. So I know for sure that's going to be a positive ratio for the cosine of A. So the whole value of this thing has collectively turned into 4/5. In fact, actually, I'm just going to draw that down here at the bottom, is that would be the value that this whole thing would have turned into. So maybe I will just put a little line that would say that would go there. So again, what we take is kind of start with the inside, picture it like it's an angle. If it helps, you can kind of picture moving whatever the inverse trig function is over to the other side and making it its inverse. So the inverse of arc sine is actually the regular sine of the angle, and then I have my ratio that then I can set up my either opposite over hypotenuse or adjacent over hypotenuse or opposite over adjacent, depending on what function was provided on the inside. But I can draw a triangle, label the 2 sides I know, find the third, and now I should be able to do any trig ratio. So even if this would have been, say, a tangent instead of cosine in front, I still would have had the ability to answer the same question without really changing a whole lot about how I started the problem. So again, to reiterate, start with the inside, draw a triangle, use that triangle to answer the actual function on the outside. Move on to this next example. Pretty much the same approach. I mean, I have different functions, but as far as what I need to do, that part's still the same. So as I mentioned, the first step is start with what's inside, draw a triangle to represent it, utilizing the function that we have, or C. What's a little bit different about this one, or what kind of pushes this one a little bit more complex than the one before, is instead of having a ratio of 2 numbers, now I actually have a ratio of something that involves a variable. So when it comes to creating my triangle, I'm actually going to have to worry about squaring that variable. Honestly, this inside part, if we again just call that maybe some arbitrary letter A for our triangle, that gives us at least a label to use. So really I'm just trying to figure out what is sine of that A value. I just need to figure out what actually can I label on the triangle. So if we kind of see what's inside here, that's the arc cotangent. Really is just telling me that ratio inside is the cotangent ratio. So if cotangent of that A is equivalent to that x over 2, we could then use that to our advantage and say, well, tangent of A should be its reciprocal, 2 over x. So that gives me my opposite must be 2, my adjacent must be x, and then I could square both, add them together, and that should give me my hypotenuse after I take its square root. So if I square each of those, I'd have x squared, can't do anything with that, add it with 2 squared, which would be 4, and then again, because it's the hypotenuse, I would then take the square root of that to get that ratio. So from here now it's just what's the sine from that triangle I just created. Well, the sine from the triangle I just created would be the opposite 2 over the hypotenuse, which we just found to be the square root of x squared plus 4. And kind of like a similar example in I think the 7.1 notes, if I recall correctly. This is a situation where I don't really have to rationalize because there still is a variable involved. So I would just leave it as that ratio of 2 over the rad of x squared plus 4. So again, I could have had this be any other function instead of sine here in front. I could technically do cosine, I could do tangent, you name it. I have the triangle labeled. I can do any of the 6 possible ratios now that I have it. So that's as the last example was, and this one as well. I just start with the inside, draw my triangle, label 2 sides, find the third, and then come up with which ratio was the actual problem wanting. And then voila, that turns into our ratio. If we could simplify, we would, but this is as good as that one really gets. For the last example here, this is about gonna push the limit as far as I can, as at least with regard to like how much this can get involved with. So this is now taking sine of 2 things being added together. So if you kind of think in terms of what really is this relating to that we've seen, Well, it's really this first part. We could say that's just some angle that would get out, right? Because I'm putting a ratio into the arc sine, which should turn into an angle, but then I'm taking a different ratio, plugging it into the arc cosine. Well, that actually would be a different angle, and then there's addition between. So if you really picture what that would be, if I just simplify what that looks like, that's really asking me to compute what is sine of a plus b with the two letters that I chose. Now again, I just chose arbitrarily a and b, but our formula has been staying with a's and b's, so I hope that's not too big of a stretch. Now for this one, it's going to require us to actually draw like two different triangles, because I have one angle that's going to be referencing angle A, and then I have another one that's going to be referencing an angle B. And for this formula, if we think about what does sine of a plus b require, that really is going to want me to do like sine of a times cosine of b, and then add it with what's sine of b, and multiply it with cosine of a. So that's where these two triangles are going to get involved. It's going to help me replace each of these individual ratios with whatever their value is. So let's go ahead and start labeling some of these sides. We also could potentially just try to figure out what the other one is. I think we probably could connect that 1/2 is probably going to be paired with a rad 3/2 from the unit circle, but again, we could just let the triangle itself kind of deal itself through. So with this one, I would end up with 1 is the opposite, 2 is the hypotenuse, and so if I go ahead and square both, take the square root, after I subtract, it would become a 4, take away 1 is 3, square root of 3, there it is, which again makes sense because a rad 3/2 likely should be paired with, if sine is 1/2, that probably means the cosine is rad 3/2. The other one though, 5/13, that's not as common. This time though, it's a arc cosine, so that's really like it's telling me the cosine ratio is 5/13. So that means the adjacent would be 5, the hypotenuse is 13, and if I went through and squared both, subtracted 169, take away 25 would take me to 144, and the square root of 144 actually is a nice number 12. This actually is one of those common, kind of like a 3, 4, 5 triangle. A 5, 12, 13 is also semi-common. Hasn't popped up a whole lot in this class, but it is technically a nice Pythagorean triple we can take advantage of. Now from here, just like we would do with a normal sine sum formula, is now I just replace each with the ratios from those triangles. So sine of a we already knew was going to be 1/2. That was kind of provided for me. Cosine of b, that one also was kind of provided for me. That was 5/13. Then I'd add it with now sine of b. That's something I needed to have the triangle for. That's 12/13. Opposite over hypotenuse, if you didn't follow that. And then cosine of a, that would be the adjacent over the hypotenuse. That would be the rad 3/2 we mentioned earlier, since it should be paired with a 1/2, since it's kind of from the unit circle. So now if we think about what we would do, it would just be multiply the two fractions and add the results together. Looks like they already have a common denominator of whatever 2 times 13 is, so I'm going to go ahead and just write that down. That's a 26. And then 5 times 1 for the first term is a 5, added with 12 times a rad 3. There's really not much I can do to multiply those together, so it really just kind of squishes together, and voila, we've got a ratio from this. So kind of key takeaway, or at least maybe a hint or suggestion I would provide for this, is if you ever notice that you do have multiple things inside of parentheses like this example, I might recommend doing like I did here with the A's and B's. Just rewrite or replace them with a letter and just see if it matches something. Hopefully once you did that, you'd kind of make the connection of, oh, that kind of resembles that sine of a plus b formula. Let's go ahead and maybe try and follow that, and then hopefully that would get the ball rolling and to the direction of, oh, I probably need to figure out 4 different ratios from triangles. And again, like I said, hopefully it would just kind of start rolling in the right direction for you as far as your thought process is concerned. But anyway, hopefully all these examples and the explanations provided therein have been helpful. But as always, if you have questions, just come find me. We can work through some extra examples as need be. But I appreciate you taking the time watching this video, and we'll catch you next time.